Okay, hello everyone. We're happy to have Bruno Vallette, and he will be speaking about new types of homotopy bialgebras in geometry and topology.
Exactly. Thank you very much for the invitation. It's really a pleasure to give a talk here. I don't know what here means. For me, I'm at the IHES, so I should acknowledge the great working conditions. I mean, it's thanks to the IHES that I can give this talk, because at home it would not have been possible. So Manuel asked me if I could give a kind of overview of the kind of bialgebras and their homotopy versions appearing recently. So I tried to do my homework. So at least I know that in some place there will be some comments that are not completely on the literature right now. So you'll get a little bit of new things, I hope. Anyway, let me say in general, okay, the general presentation is as follows. I will go slowly at the beginning. You see state of the art, infinity algebras, and I will review what it means. So no problem about that. But just to say that a bit of history, was that in the 70s, Jim Stasheff, in his PhD thesis, he discovered this beautiful new notion of the infinity algebra. Okay, cool. And then gradually over the last century, you had more and more algebraic structures appearing in the homotopical version. I don't know what you heard about, but homotopy commutative algebras, homotopy Poisson algebras, homotopy Gerstenhaber algebras, whatsoever. Okay, good. And then some machinery was developed to treat all these types all together at once, this theory of operas. And nowadays there is something quite new appearing, which I haven't seen before, is that now we're looking at bialgebras, that is operations with several inputs and several outputs at the same time. Of course, since we're doing algebraic topology or algebraic geometry, etc., working with chain complexes, we need a homotopical version of this. And okay, then how do you do that? Well, you can try to do it by hand. Good luck. I'm by far too stupid to do that. And so you're lucky, I mean, today, 2024, you're quite lucky because the theory which encodes this type of bialgebras has already been developed. So we can use it. And the purpose of my talk is this, is to show you 3 new types of bialgebras, quite interesting, coming from completely different perspectives, and they share some relationships, and we have all the formulas, not only the theory, for their homotopy theory. So, okay. So here my talk will be mainly based on this joint work with Johan LERAY. Do you see my mouse if I move it? Yeah, good. So this is joint work with Johan LERAY that you can find on the arXiv. And there are many other papers. This is kind of a survey. There are at least 2 papers I will refer to quite often. This paper of Kontsevich, Takeda, and Vlasopoulos, and the recent paper of Alexandre Kenney. And there are 2 other papers I will mention, but this will come in the text. Okay. Of course, if you have questions, you stop me. You will never interrupt me. You stop, okay? Just otherwise I will blah, blah, blah all the time. So I thought it would be good to start with the mother of homotopy algebras, infinity algebras. Okay, what's that? Well, let's say we're doing topology and we want to recognize the homotopy type of spaces, and well, it's a difficult problem. So what do? We attach in a certain way to certain topological spaces some algebraic structures. Okay, well, so what can we do? Well, we can of course compute the number of connected components, we can compute the Betti numbers, blah, blah, blah. Okay. And then one step higher is we take a topological space. K can be a ring, but please keep in mind that in the sequel, very often I will work over a field of characteristic 0. And then you can look at the cochain algebra of X. So here, for instance, I consider the singular cochains on X with coefficient in K. Cool, it's a chain complex with a certain differential D, good. And then you can define, I will reproduce the formula, a cup product there. Good. It has combinatorial, it's a combinatorial formula, good. And you check this guy is associative. So for me, associative means this. Okay, you compose 2 guys with the third one, and it's the same thing as composing the last 2 guys with the first one. So it's associative. Okay, good. And since D is a derivation with respect to this guy goes down to the cohomology. The cohomology groups, you know, they're defined solely by the D, okay? And then this cup product induces another cup product on the cohomology. So again, we have a cohomology algebra. And then we know that if we can compute, we take two different spaces, and if they are not homotopy equivalent, and we get two different cohomology algebras, then, well, we know how to detect in this way that the X and Y are not homotopy equivalent. You see, I wrote something in red, which means, well, be careful. This is the be careful sign in France. This is for when you go on the road. You have two dangerous curves. Be careful. This guy is associative, and I want to say that's my vision for a bad reason. Okay, it has no reason to be associative in some sense. It's more than that. It is just that the failure of associativity does not express itself. I will come back later if you've never seen that before, but keep that mojo in mind. Okay, this guy is associative for a bad reason. Conceptual bad reason. Okay, so this is exactly what I've been saying before. That is, how invariant are these constructions? Okay, if you take a continuous map of topological spaces, the cochain algebra, it's contravariant. Okay, they're sent to one another under a morphism of the G algebras. All this story is perfectly coherent. Good. And then if we're interested in looking what we can recover from on the cohomology level, then what we want is, when do we get isomorphisms on the cohomology level? Well, you know, you're quite lucky, because if your two spaces are homotopy equivalent, so if this is a homotopy equivalence, then this guy induces an iso here, and people call that a quasi-iso. It's not really an iso, it's an iso just on the cohomology level. Okay, good. And again, you get a map in, I don't know, now you get a map in DG algebras, except there's no D where D is 0. So it's just a map of associative algebras. Good, perfect, it works very well. But now you see, somehow we opened Pandora's box, because we want to compare DGA algebras, differential graded associative algebras, up to this notion of quasi-isomorphisms. Okay, so now, being quasi-isomorphic for two DGA algebras, is that an equivalence relation? No. And this failure forces us to, when we want to understand the homotopy theory of DGA associative algebras up to quasi-iso, it forces us to localize with respect to quasi-iso. Okay, it's not a big deal. We're grown-ups. Oh, whoa. What did you do? Don't give me a second. No. Wait, it does not scroll continuously. Oh, no, I have to be careful. Okay, sorry. Voila. So what does it mean? So we now are going to consider the, if you want, the current relation generated by being quasi-isomorphism. So we, in the localization, formally invert quasi-iso. And this can be quite messy now. The homotopy category, it's a localization, etc. So how can we understand that? Isn't there an easier way to understand that? Okay? And yes, there is one. And you see, again, this be careful sign. Passing to the associative algebra structure on cohomology, we lose a lot of homotopical data. That's why I said it's associative for a bad reason. There are some shadows behind that. If we just consider this cup bar, we lost all of them. Okay. And the solution came from many people, but I definitely want to cite Jim Stasheff and Kadeshvili. Jim Stasheff came studying the loop spaces. He came to the notion of A infinity algebras. And I will say Kadeshvili developed quite extensively the properties of this A infinity algebra. So what does it look like? Well, an A infinity algebra, the idea is, well, sometimes the heuristic is very simple. You have a binary associative product on a space, big chain complex, and then you deform your chain complex. You have a de-Friedrich of chain complex. So you deform the underlying guy. What about the algebraic structure? It gets deformed too. There's no chance that the guy you get on the deformed guy is associative again. Okay, so mu2 will not be associative. The 2 stands for the number of inputs. And instead, you still want to control how far from associative is mu2. So you have an associator, well, it's not Drinfeld associator. It's an operation with 3 inputs. Those differential is the left composite of mu2 with itself minus the right composite. In general, an A infinity algebra encodes all of this coherently. You have a first homotopy, a second homotopy, etc. A mu3, a mu4, a mu5, etc. So in general, it takes the following form. You have a chain complex with a binary operation of degree 0. An operation of arity3, which is of degree 1. It's a homotopy for the associativity relation. And the homotopy for the homotopy, etc. They all together, they satisfy this. If you look at derivative of mu n, that is, you do d here plus, voilà, plus minus. Okay, here I will make no sign explicit. Okay, so you work over F2 if you wish. Well, I said field of characteristics 0, but forget. D plus D plus D plus D plus D. Okay, the derivative of this is the composite of all the guys before. Okay, so if you do D of mu3, you get the left comb minus the right comb. Okay, so this is an A infinity algebra. Okay. So what is it good for? Well, first, there is a cute way to encode that. It admits a deformation theory flavor. This is nothing but a Moore-Cartan element in the Hochschild cochain complex. So you can do depth theory of an infinity algebra that way. Cool. I don't know, you will tell me, well, you know, now you have a notion of algebra, but you would like to have a notion of morphism too. Okay, yeah. And the notion of morphism admits the same kind of definition. It's not just one map. It's a collection of maps. Again, the heuristic still holds. A morphism of algebra is one map which strictly commutes with two operations. But now, if you want a notion of two homotopy, you'll have one map that does not commute, so that the two products don't commute, but up to a certain homotopy, etc., etc. So it's the same thing. So I don't want to afraid anyone with this formula. If you've never seen it, let me try to see what it means. What is an A infinity morphism? You take two associative algebras or A infinity algebras, if you wish. And an A infinity morphism is a collection. It's a collection of maps from A times n to B, or n equals 1, 2, 3, etc. Okay? So if you wish, you forget the formula. It is just saying the following thing. Do a first bunch of F, then you go from A to B. And now when you're in B, you do the product in B. Or you can do things in the other way around. But you see, because of degree reasons, you cannot saturate with mu's here, if you wish. So you do just one mu at the source, and then you do F. So this, you have inputs in A, and then you go to B. That's it, okay? So, for instance, if you write this equation for n equals 1, you get that f of d is equal to d of f. So f1 is a chain map, etc., etc. Well, so it behaves well. You just have to keep in mind, you have to allow yourself, you have to be open-minded and say, okay, I admit, when these guys want to do homotopy theorem, they have collections of maps, structure operations. Alors, okay. So why is that good for? No, I wanted another theorem before that. Sorry, excuse me. Where is it? Oh, I lost it. Ah, man, what is this been doing? Sorry. It's on. Let me remove the. Sorry, let me do it that way. Voilà. So why is that good for? And let's go back to this, to what we looked for the, for instance, you can take here the homology, but otherwise, no. This is the heuristic I mentioned before. You take a chain complex and you have a deformation retract to another one. It can be the homology, but not necessarily. And then this nice homotopy transfer theorem due to Kadeshvili says, well, you know what? If you endow this big guy with an A infinity algebra structure, you can promote this entire data in the category of A infinity algebras. Okay, I didn't mention A infinity morphisms can be composed in a very natural way. What does it mean? It means that here you start from an A infinity algebra structure on A. Fair enough. How can you transfer it to H? Well, you can take guys from H, okay, view them in A, multiply in A, and coming back to P. This is too naive. You have some perturbative formula, which now produce a genuine A infinity algebra structure. The naive one I mentioned does not work in general. It works when D is equal to 0, okay? So in general, what you have to keep in mind is A infinity algebra are stable up to homotopy, which means if you start from one, you deform your space, you get a transferred A infinity algebra structure on the smaller guy, such that, because otherwise the statement would be empty, such that your quasi-isomorphism here and your quasi-isomorphism there, you can promote them into A infinity quasi-iso. And moreover, you can also promote the homotopy into an A infinity homotopy, okay? So this is super coherent now. You see, this algebra homotopical world is super coherent. Associative algebras, they're not. If you start from an associative algebra, what you get here, if you want to lose nothing, you get an A infinity algebra. You'll tell me, well, but if I have the homology, well, okay. Alors, sorry, this is what I wrote here. If you look at the cohomology, for instance, you can fully transfer an A infinity algebra structure, and these are the Massey products. For those of you who know what it is, they detect the homotopy type of X, okay? So it turns out that on the cohomology level, you do have an A infinity algebra. It is just that D of nu 3 is equal to the associator of nu 2. Well, but D is 0, so the associator is 0. Okay, so that's why I wanted to say the associator is 0 for a bad reason. It is not that nu 3 is 0, it's that it does not express itself. But nu 3 is there. The triple Massey product is here. It encodes some data, so don't lose it. Okay, voilà. And here is the explicit formula for the transferred structure, which is quite nice, I think. So what do? You see, I did not stupidly, naively look at I, mu n, and then p. Then take the sum over all planar trees. And how do you interpret these guys? You take n elements from H. With the map I, you go into A. Now that you are in A, you can do your beloved products, mu5, mu3. But then if you do this, first, your composition scheme does not have the good homological degree. It turns out that you have to label the edges by the contracting homotopy. Okay, this is what is perturbative in some way. Okay, that's it. Okay, and then you can work with that. Okay, and this is the formula that you have for the Massey products, for instance. Okay, so that's it. Okay, if you've never seen that, I want to tell you, it's not complicated. Take some time, you can recover that, you can work with that. We have all explicit formulas and it works perfectly well. And then these A infinity algebras and morphisms, they satisfy nice properties, the homotopy transfer theorem. And the last one is, well, now we are in the notion of morphism is wider, okay? So we have more space, okay? And look, how do you invert 1 plus x? How do you invert that? But you have to look at the series, okay, or 1 minus x, let's say. You have to do 1 plus x squared plus x cubed, etc. It is the exact same thing here. Why can't you get an inverse of a quasi-iso of associative algebra? Because you have no series. Well, but if I work with A infinity morphisms, this is a series. That's it. Any quasi-iso of associative algebras, but more generally, any A infinity quasi-iso admits an inverse. And really, if you write down the equation, it's just the inverse of a series. Cool. And why do you like that? You like that because sometimes you want to prove some formality theorems. You want to prove that two invariants in algebraic topology, they encode the same data, etc. And how do you do this? You want to show that there is a zigzag of quasi-isomorphism. It's pretty complicated to do this. You have to be Maxime Kontsevich to solve the deformation quantization of Poisson manifold by because here you see what you have to construct. You have to construct an intermediate algebra. So, wow. And no, you see, this statement is much more simple. Why? Okay, you'll tell me I'm a bit cheating. Here, maybe I have 8 maps, and here I have a series of maps. Okay, fair enough. But I construct no space. And constructing a space is, I believe, more complicated than just constructing an assignment, a map. So this is really a reduction. You would love to do that. Okay. And then let me mention So I'm sorry, I should mention results of Manuel and other people, but you wanted to hear something new. So here is something new. Is that good? I mean, shall we consider just A infinity algebras? Okay, is that enough? I mean, people mention E infinity algebras, and very complicated stuff. No, stay on the A infinity level. You're fine. And this is a recent theorem by Campos, Robert Nico, Petersen, and Viestra. And what does this theorem say? It says, well, you know, this coalgebra, this cochain coalgebra is quite good. It faithfully detects the rational homotopy type of connected nilpotent blah 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 spaces. So wow, okay, you don't need to go further. Just that. Okay, cool. So you see, A infinity algebra is enough to encode rational homotopy type of spaces. Wow. Okay. Is there any question before I go further? I plan to go beyond the infinity algebras, but if you have questions on this, feel free.
So there's a theorem behind this theorem, right?
Yeah.
Right. I mean,
Yeah.
yeah. But you haven't said anything about C infinity or commutative.
No, I don't want. I don't want. You're right. I can say it. Okay.
No,
Okay. Let me say one word. I mean, again, since I am in the where everything was
I just said it
created.
because it's an important result in the theory, right? So we should emphasize it. Yeah.
Yeah. So let me say, usually what people consider to get the rational homotopy type, they use Sullivan algebras, and Sullivan algebras, they are commutative. Where is commutative here? And the deep result, this is just a corollary in that paper, but I like it. This is a corollary of the following statement. If you have commutative algebras, so commutative associative algebras, and you want to check their formality, it is enough to check it in the category of associative algebras. So two commutative algebras are formal if and only if their underlying associative algebras are formal. Oh, this is a beautiful theorem. Voilà. So now what I would like to do is to go beyond. So recently, okay, you see, to detect the homotopy type of spaces, let's say A infinity algebra is good for you. Why not? But I want to do more. So, and this will require more algebraic data, more algebraic structure. For instance, you have an oriented manifold. Okay, good, fair enough. And you want to encode the Poincaré duality. So not only the topology of your manifold, but also the Poincaré duality. And it turns out that if you use the Tom class, again, IHS, there exists a beautiful element, symmetric element in the cohomology algebra. Okay, so I don't know if my notation is people do understand. It lives in H times 2, but it's symmetric. Okay. Voilà. Bon. And well, then you can check because you know this guy is equipped with the cup product, so it was already an associative algebra. And what does this symmetric bitensor satisfies? And it satisfies the following relation. So you see, well, I am operatically minded. So for me, everything is operations from A times something to A times something. So what is an element? An element is a map from A times 0, which is K, to A times 2. And I view it as a box with no input, because it's A times 0, but it has two outputs, and they're symmetric. Okay, I hope it's okay for everybody, because then I can be super lazy. Oh, I should have written an equal sign here. So what is the compatibility between the associative product and this element induced by the Tom class? Just this, okay? So you do the product like this, it is equal to doing the product on the other side, okay? What matters here is that your product is definitely not commutative. Okay, you can tell me, but it's stupid. I mean, I cannot detect which one is left and right from the box. Okay, but what matters is that here I put this guy on the left, and here I put this guy on the right. So this is really different. And these should be equal to, come on, it's pretty easy, no? Okay. And this was named V-algebra by Tradler and Zenalian in 2007, as far as I remember. Maybe I make a little mistake. Okay, example of the cohomology algebra. So you see, voilà, here is another example. You want to encode more than associative algebra, you do that.
Bruno, is this equivalent to a Frobenius algebra? Oh, maybe you need like unital or something. And
Yeah. So no, exactly. We have to be very careful when we start adding curvatures, co-units. Then we can rewrite things. But then without, we have no space to rewrite these guys. So no, I don't think so. Okay. Then another context. I would mention three. So this was one. Two. What do you do when you want to do non-commutative Poisson geometry? Let's go slowly. Sorry, let me hide. What is classical geometry? Functions on your manifold M. It's a commutative algebra. Perfect. The heuristic of non-commutative geometry is that you should replace that by any associative algebra. This should be your space of functions on a manifold, okay? Not read the red part yet. Then what do you do when you do Poisson geometry? So when you do Poisson geometry, you have a manifold, and the Poisson structure is more. It's a bivector field which squares to 0. The bracket with itself is equal to 0. Once you have this, you can endo your algebra of functions with a Lie bracket, which is called the Poisson bracket. It is induced by this data. Okay. And all together, they satisfy something. This is a commutative algebra. This is a Lie bracket. And this is a derivation with respect to that. It's usually called the Leibniz relation. If you've never seen that, just listen to the music, okay? No problem. Because this is not what I want to review. What I want is what's on the right-hand side. Now, how can you do non-commutative Poisson geometry? You should generalize this in the non-commutative context. Okay, so first, there should be a notion of non-commutative bivector field satisfying a Moror-Cartan equation. This is a Moror-Cartan equation. Okay, it exists. I don't want to review that. I just want to say that Michel van den Berg proved that the existence of this is equivalent to something, which is the analog of this guy. Okay, this guy is an operation which eats two inputs and creates one output. It turns out that in the non-commutative setting, you have a map which eats two guys and produces two guys. Why not? And he called that, dump that. This is a double bracket. Okay. And now I can comment on this red part. The heuristic, heuristic behind non-commutative geometry is that all the constructions you want here, I mean, they should lift in a certain way the classical case. They should lift it as follows. When you get your associative algebra and you pass to the affine scheme of representation on A, these structures should give you something like this. And it is the case here. So it's a coherent lifting with respect to this Kontsevich-Rosenberg principle. Okay. So this is doing the job for you. And I want to keep that. Okay. So since I want to keep that, let's give it a proper definition. A double Poisson bialgebra, I cut it gebra. It's an associative algebra, but now I will not endo it with a Lie bracket. I will endo it with this operation, which is an operation with two inputs and two outputs, which is cyclic symmetric. You see, if you turn it around all together, the inputs and the outputs at the same time, then you get a minus sign. Okay, but you have to switch the inputs and the outputs at the same time. It has to satisfy a certain Jacobi relation. If I had an operation with two inputs, Jacobi will be this comb and cyclic version of it. This is the analog. I find it quite clear. And then you have the same Leibniz relation. Okay, this should be equal to 0. So this guy should be equal to the sum of these two guys. You see? Which means that if you fix this guy, fix this guy, fix that guy, then this becomes a derivation with respect to the associative product. Okay? So it's definitely a Leibniz relation. Okay? The operator, the linear operator, where you fix, what am I saying? Yeah. You fix that and that, it's a derivation. Voilà. And that's the notion of a double Poisson algebra. Again, it's an associative algebra plus something else. Okay? And now let me review a third example coming from quantum algebra and discrete geometry. What can you do? Well, now Drinfeld said, well, if you now look at functions on the Poisson Lie group, okay, what do you get on this guy? Well, you get a Lie bracket and a Lie co-bracket. Okay? So a map with two inputs, one output, one input, two outputs. Okay. And what are they supposed to satisfy? This is supposed to satisfy the Jacobi relation, and this is supposed to satisfy the co-Jacobi relation. You just write it upside down, you have it. So the sum of three terms equal to 0. Okay. All the possible ways, the three possible ways of composing this guy with itself, the sum of these three guys, 0. Okay, good. And they have to satisfy a certain condition. The composite of 2 is equal to the sum of all the possible ways to invert them. Anyway, forget, again, this is just for the music, okay? I just want to tell you there is a new word that exists and we know how to control it. So if one day in your math you encounter that, you send me an email, okay? And then this is supposed to coincide to the classical case, okay? Now what would happen if I want to quantize this? And we want to quantize that, we want to quantize into a notion which is not the integration of it, but so the quantization actually should take the form of an associative bialgebra. That is, an associative product, a co-associative coproduct. And then you want to ask that the coproduct that goes from A to A times 2 is a morphism of algebra. Alors, you'll tell me, okay, this guy goes from A, I have an algebra structure, but what is the structure on A times 2? Well, you take two guys, you multiply the 2 first, and you multiply the 2 second. And saying that this guy is a morphism with respect to this means you do the product in A and you do the coproduct, you do twice the coproduct, and you do, this is the multiplication for A times 2. Okay. So this relation just amounts to saying that the coproduct is a morphism of algebra. Okay. And this is what is produced by this quantization of Lie bialgebra due to eating of Kazhdan, and for which we'd like to have a universal explicit formula, etc. And then you'll say, okay, this is nice. I know a lot of bialgebras in, for instance, algebraic topology because I know Hopf algebras, etc. Then this condition of being a morphism, sometimes we like to have an infinitesimal version of it. And instead of asking that we have a morphism, we can ask that we have a derivation. Okay? And what does it mean to have a derivation? And this is a definition which was actually predates Drinfeld's work. You can find it in Johnny and Rota's work in the 70s, as far as I remember. And Marcelo Aguiar worked extensively on it at the beginning of the 20th century, 21st century. Marcelo is a young guy. Infinitesimal bialgebra. What's an infinitesimal bialgebra? Associative product, co-associative coproduct. And you ask now that your coproduct is a derivation. Okay, so it's exactly this condition. Okay, it's a linearization of this thing. Boom. Now you can ask, well, that's cool. Now I would like to go back to Lie bialgebras. So what can I do? I take my product and I skew symmetrize it. Okay, do I get a Lie bracket? Yes, of course. Your product is associative. So the skew symmetrization of an associative product gives you a Lie bracket. You're fine. You do the same thing upside down. The skew symmetrization of your coproduct gives you a Lie co-bracket. Cool. Now, does this satisfy this equation? No. And for this, you need an extra relation on the level of your infinitesimal bialgebras. These equations, and I think it's Marcelo who called it balanced. So they are balanced, they're stable, they are so balanced infinitesimal bialgebra. Okay, why not? And sorry, and Marcelo proved a very nice theorem about the existence of CD index of polytopes using this. So you see, it's not something that comes out of the box and you want to study. No, it comes from somewhere, etc. Okay. So now we have these three new notions of bialgebras. I hope you're a bit convinced that they are, say, useful because they're coming from somewhere. Now you can tell me, okay, what we would like is to compare them. And so far, they seem pretty different. I mean, you see, they come from different perspectives, etc. So let's try to compare them. What can we do? I don't know. I'm spoiling. Yes. Okay. If you take a V algebra, okay, they are all equate with an associative product, so no difference here. Okay, but if you have a V algebra, you have this symmetric guy, bitensor. And what can you do with this? You can say, hey, look, I can compose the symmetric bitensor and compose it with the associative product, okay? Cool. And if you count, 1 input, 2 outputs. Hey, it looks like a balanced, infinitesimal balanced bialgebra, huh? No, no, it's not a derivation. Man. Oh, too bad. Similarly, now you have a guy with 1 input and 2 outputs. What can you do? You take your guy with 1 input, you compose it with the guy with your associative products, and here you get an operation with 2 inputs and 2 outputs, okay? Cool. But this guy has no chance to satisfy the cyclic symmetry, okay? So you have to cyclically symmetrize it, okay? You have to take the sum of this minus that. Why not? It gives me an operation of 2 inputs and 2 outputs. Perfect, which is cyclic symmetric. Perfect, but no. Now, it does not satisfy the Leibniz relation. So no. So far, like this, these words are too tiny to accept maps from one to another, okay? So more generally, you can work, and this is what I said before. Alors, if you've seen that before, cool. If you have not, don't be ignorant. There is a conceptual...
Bruno, can I interrupt you?
Sure, always.
Yeah, I'm not sure if this is the right moment to say this, but there's a passage that you can produce an infinitesimal bialgebra from a V-algebra, right? You can take Hochschild homology.
Ah, okay.
And this is similar to string topology and so on. I mean, I know it doesn't fit with this philosophy that you're trying to explain, but I just mentioned that it's very natural. It's like forming a necklace algebra and so on, right? Yeah.
No, alors, thank you very much. I will make another comment later, but I didn't plan to make that comment. So you're right to make it. But you see here, I put a constraint. Maybe I should not have. I put the constraint that I don't want to change the underlying space.
I see. Okay.
People should be open-minded. You're right to consider what you're, but here I said no. I said no. I said I just want to be as stupid as possible, take the same underlying space. I say each time I have, you see, I have an associative product. The only thing which changes is this new bit of data. So can we compare them stupidly? No, we can't. Though you see they look like the same. I mean, this is a guy. From this guy, we can produce a guy with 1 input and 2 outputs. From this new bit, we can construct no. Okay. So thank you. Yes, sometimes you have constructions which allows you to go from one to another. But here I want a functor of algebras which comes from a map of operas. And this does not change the underlying space. That's one constraint. Okay. So, okay. For you guys, if you have heard about that, there is now, you can play with algebras by hand, but it's quite complicated. And when you want to prove certain statements, it's at least for me, it's impossible. And there is a machinery, conceptual machinery called operas, which encode algebraic structures with several inputs and 1 output for you. And this is absolutely great to work there. Everything works super well. Anyway, except that you have to learn the definition and see how it works. But then when you want to encode operations with several inputs and several outputs, operas cannot do that job. You need to consider something bigger. And there are several notions for doing this. The first one which appears was called prop. If you want to consider a connected prop, that's what I call properades, because then your composition graphs are connected. And then if you further restrict to composition graphs which are genus 0, it's called dioperad. If you know about this, otherwise, it's not difficult at all, but please allow me to work there because things are much more simple. Okay. So there is a properad or a dioperad which encodes the algebras. There is a properad which encodes infinitesimal algebras, and there is one which encodes double Poisson. And then you can go back and forth and try to look for a map of properads. And when you have this, you get a functor from the categories which do not change the underlying space. And no, it does not want to work. We've seen that, okay, we've seen these two directions. No. You can say, oh, maybe I can go in the other direction, but no, Because how can you produce a guy with 0 input from an infinitesimal bialgebra? There's no space for this. So if you stay on that level, it does not exist. But, well, the only statement you can make is, okay, you put this guy equals to 0, you put this guy equal to 0, and then yes, of course, but then the only thing you keep is the associative algebra structure. Okay. And the big jack in the box, I don't know, Deus ex machina is, wow, but if you pass to the homotopy versions, which I'm going to describe later, but I want it to be as fun as possible. If you pass to the homotopy versions, sure, they're super coherent. Okay, so their homotopy version includes A infinity algebra, A infinity algebra, A infinity algebra. But moreover, you will have homotopies for the relations. So here, between the A infinity algebra structure and this symmetric bi guy. Here you will have higher homotopies for the co-associative coproduct. So you have an A infinity algebra, a co-infinity algebra, and homotopies for their relations. Forget, I will not describe that for you. I just want to tell you that now we do not have just one collection of homotopies, but many, okay? Still, this collection of homotopies can be fully recovered from this, and they can be fully recovered here. What I want to say with no technology or whatsoever is that the operations that define what is a homotopy double Poisson algebra, you have to add a few more, keep them, and you have to add a few more to get this notion, and you have to add a few more to get this. Wow.
So Bruno, are you allowing genus here?
No. It's genus. Yeah, I should have. Yeah, it was too much. I should have written V genus 0.
Okay, and so is that the same as saying? Is that the same as saying the considering this as dioperads or not?
Yeah, exactly.
Good.
Exactly. Here I can have genus, but causal duality is going to kill it. But here it matters. So if you hide V infinity, if you consider Calabi, yes. Otherwise, for V infinity, I consider the dioperad version. I wrote it later. I forgot here.
Yes.
Yeah.
Good.
Maybe I should cut short here because I want to tell you what I can do with this. Just to tell you, and this is well explained in the introduction of Alexandre Quesnay's paper. So with Johan, we did, hi Johan, we did this map directly, and recently Alexandre did by factorized. If factors this guy. So okay, anyway, we did what doesn't matter. Anyway, the idea is what? The idea is on the strict level, nothing exists. On the homotopy level, something exists. Yes, but there is a place in between the two. And for those of you who know what I mean, they will understand. The other ones, again, listen to the music. How do you produce the homotopy versions? You start from your operad and you cook something that is called the causal dual. And it is between the causal dual that will have spaces to define maps. Okay, so any of these infinity versions are produced by free guy on the causal dual. In the theory, this is called the Kobar construction of the causal dual. Voilà, that's it. Okay, so how do you compute this causal dual co-guy? You compute the causal dual guy because nobody knows how to work with co-algebras, co-operas, co-properatoires. Anyway, wow. People know how to work with them, but to compute them is difficult. So what do? We start from an operad, properad, whatsoever, with generators and relations. And for the dual, the causal dual, we take the linear dual of the generators and the orthogonal of the relations. Why not? Okay, that's it. And then if you do that, this is this slide. So I did the computation for you. What is the causal dual of V? You take the same. You see, I put the original operations in blue and the linear dual in orange, so that it's not confusing for you. You see, because they look like the same, just they have the same shape, but the color tells you where they live. So here they are in the linear dual. So for instance, for V shriek, it's V. They satisfy the same relations. Up to suspension signs, please, let's hide that under the rug. if you look at the causal dual of infinitesimal bialgebras, well, it satisfies the same relations, except that now your derivation becomes a fully rewriting thing. All these guys are equal, and then you kill the genus. That's why you get a dioprad, because in the causal dual properad, you kill the genus. Okay. And then this is the formula for Poisson. Okay. And if you do this, now you do what we were doing before. You do send your coproduct to this. Okay. You do send that to that, and now it works. Okay. So you see, on the causal dual level, you have space for genuine maps. This is an embedding. This is an embedding. If you look at the linear dual, you have projections, and it produces exactly this under the Crowbar font, period. Okay. This is not necessarily well explained in the literature, except in Alexandre's paper. It's not well explained in our paper. So you see, my mojo is more degrees of freedom on the causal dual level. Cool. Sorry. So before to proceed to the last part of the talk, let me give you some kind of state of the art of what is known about these structures, because they seem super close and cool. Kate and Poincaré, they proved that the dioprad V is causal, genus 0 part. What about the higher genera part? Nobody knows. The notion of V algebras was rediscovered or given other names by Paul Seidel. He calls that A-infinity algebras with boundary, and pre-Calabi algebras by Kontsevich, Vlasopoulos, and Takeda. Johan, oui.
Can you say a word of what being causal would imply for this proper?
The first, what implies, it implies that this construction is a resolution of V, is a cofibrant resolution of V. It means that here, this guy always comes equipped with a map to V, and it's quasi-iso if and only if causal.
I see. Good.
Cool. You get a super nice resolution. Thank you. Sorry, I'm going very super fast on causal duality. And it's a crucial property. Without that, you don't know that the two homotopy theories are the same. Okay, the properade des Poissons is causal, and nobody knows whether the properade of infinite. So if you want some nice subject to study, study this. This is quite nice. Let us know, please, because we are considering this these days. But okay. One word. They're super close, these notions. Okay, and actually the projection is not. I mean, it's very tiny, the difference between these three. And when you pass to the world with curvatures, so I'm adding curvatures, I'm not describing it here, then they become exactly the same. So you see, before, without curvatures, they're super close. And this is what we proved with Johan, and we liked that theorem very much. Also because it allowed us to meet quite often. This showing that this guy is the same thing as this guy tells you that when you want to define derived non-commutative Poisson geometry, the two definitions are multi-vector and the structure, they are the same. So this isomorphism admits this interpretation. Any way you define, there are two different ways to define derived non-commutative geometry, they're the same. Okay. Now, maybe you want to see what they look like, because, well, we were able to say what were A-infinity algebras, okay? So a homotopy curve, blah, 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 blah. So any of these three is what? It's a bunch of maps. You have lambda 1, lambda 2, lambda m inputs, and 1, 2, m outputs, okay? And here, m has to be greater than 1, and all the lambdas are to be non-negative, okay? They are supposed to satisfy this symmetric cyclicity, okay? And then they are supposed to satisfy some quadratic relations. Do not look, this is ugly. So you'd better see what I just wrote here. First, there is another equivalent definition of V infinity algebra. As you take a cyclic or a curved cyclic A infinity algebra on A plus A star, such that this is equal to 0, okay? But you see, I mean, it's like this cyclicity here. Why writing it in a properadic way? Okay, and this is what Kontsevich, Takeda, and Vlasopoulos did. They said, hey, this is stupid. Write them as roundabouts. You have roundabouts. They have the cyclicity given. you put the inputs like this, output, input, output, input, output. That's it. You just have to, you see clockwise and counterclockwise, but forget. So see this guy, I'm going to interpret them like this as roundabout. And if I interpret them as roundabout, what is their quadratic relation? The derivative of a roundabout operation is the sum of all the partitions. You partition these into two. So this is you interpret the white guy as the first operation. So this is an operation with 1, 2, 3 input, okay? And this operation has two outputs, this one, and one which is going to the second operation. That's it, okay? Voilà. So this is the definition. Okay, so it's again like for A infinity algebras, it's a collection of maps satisfying a quadratic relation. You compose in a certain way two previous operations. Now, if you want to see what is the difference between pre-Calabi or V infinity algebras, here you see I put for you the genus 0. Homotopy infinitesimal balanced bialgebra or homotopy double Poisson algebra. What's the difference? So before I said this is the curved homotopy blah, blah. So the constraint was m has to be greater than 1, and the lambdas they can be 0. I have no problem with that. Okay. Now, if you want pre-Calabi algebras, you take the guys before with their relations, but moreover, just for what m equals 1, you should ask that lambda 1 is greater than 2. Okay. This kills the curvature if you want. Okay. Now, how smaller is this notion? Not that much, look. The only restriction passing from here to here is to say, now I want n to be positive. So for me, this is super close to that. You see, you just kill not that much. Well, you kill some. For instance, you kill Poincaré duality.
What was n? N? I got lost.
Sorry, it's the sum of the lambda. It's the input. N is the sum of the lambda. Sorry.
Of the input.
N is the sum of the input. M is the number of output.
Okay, good. Yeah.
So you see, when we think in terms of how many operations we have, okay, we're just killing a few. But you might not like that because this is killing the Poincaré duality. Okay, the Tom class, it does not survive this. But still, you see, bon. And then when you pass to double Poisson, then you have to ask that your lambda are positive. Okay, I have maybe 5 minutes, I think, to do the last part. Again, well, let me make one comment. There is a nice series of video in France, which is called Voyage au pays des maths, trips to the country of mathematics. And it's a series of video for kids to know what mathematics are. And it's definitely not stupid. Huh? They explain the Poincaré conjecture, etc., etc. So, and the guy says at the beginning, we are going to make a trip in the country of math. We will not do math, just listen to the music. So it's the same thing here. Just listen to the music. I mean, I will send you the slides, etc. Okay. Can we do homotopy theory for these new types of homotopy by algebras? Yes, in the exact same way as for A infinity algebras. Okay, well, we have to find the good generalization, the good way that leads to generalization. Same way. Okay. First, if we were working with algebras, this is all known. I mean, the theory of operas, the operatic calculus, gives you infini-morphisms, homotopy transfer, etc. Okay. So for any algebra, one output, which is cobar of a co-operad whatsoever, it is well known. Okay. So this is really well known for. Okay. What is new? I mean, for instance, you have some things in the book with Jean-Louis. But what is new these days? So this is 2020, this paper. We were able to extend everything on the level of algebras, bialgebras. And of course, we're working with properas now. So now any category of algebras encoded by cobar of coproperad, we have it. There are things that are a bit different, but anyway, but we have all the formulas we have everything. So I didn't want to bother you with the theory itself. I want to show you how it works. And then you'll get a little bit of example, the three above properads. Okay, alors, properads or dioperads for V, okay? If you consider genus 0 dioperad, if you consider the full guy properad. But for these guys, you don't need this sort of thing. Okay, first, for all these three guys, there is a higher Orchil complex, okay? Those Maurer-Cartan elements are exactly pre-Calabi algebras, homotopy involutive, homotopy infinitesimal balance by algebra, and homotopy double Poisson by algebra. Okay, I didn't plan to cover that. I plan to explain a little bit more their homotopy theory. Okay, here it is. What is an infinity-morphism? Like a infinity-morphism, again, it's a bunch of maps that go from A times lambda 1 plus lambda m to B times n, okay? And what are they supposed to satisfy? You take your roundabout, okay? So for any roundabout, you have a relation, and you take your roundabout, and then you, now what am I saying? Yes, for any roundabout. And now what you do? You take all the partitions, so you draw arcs like this, chuck, chuck, chuck. And when you draw arcs, you get guys that are white here, and then at the interior, you have a gray area, okay? How do you interpret this? The white part, you apply your map. So you go from A to B, okay? And then you do nu, and nu goes from B to B. So several, one. And dually, you do the same. You do first mu, you do one, and then below, you do several f. That's it. I mean, kids can play with this. You can take your kid and make it draw arcs. He will do it. What's the formula for the composite of infinity morphisms? Same thing. You take your roundabout, and you take bicolored partitions like this, okay? You draw arcs such that they have to alternate in colors. This is very important. This is that. And why? Because then you can interpret the white part as a first layer of F, and then you interpret the gray area as another level of G. So you go from A to B, and from B to C, period. And this is associative. Voilà. It's associative because you're going to partition this roundabout, and then you're going to further partition this roundabout, or further partition the other one, etc. So it's pretty clear. Well, I hope so. I'm almost done. The homotopy transfer theorem I mentioned of Kadeshvili, etc., many people, but Kadeshvili was definitely the first one. We were able to extend it. Okay, so here, this slide, I did a copy paste. So except I changed A infinity for P infinity. So the same. If you're still awake, you'll see that there is one, but you can still see some traces that I erased. There should be a formula for the extension of the homotopy into blah, blah, blah. This is more complicated, so we don't have it yet. But still, I mean, we have the transfer structure, and we lost nothing because we are able to connect them. Oh, there should be an arrow here. Connect them via infinity quasi-iso. So same way. And if you want explicit formulas, we have, okay? You start from a pre-Calabi or whatsoever on this part. What is the transferred structure? You take the sum for any roundabout. You take the sum over all the partitions of your roundabout. And then here, each time you have this, you interpret it as a roundabout, so as an operation on A. And here, you label this row by H, 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 H. So this is the Kadeshvili's formula, or I would say Kontsevich-Zoibelman for this, because it's maybe they were the first one to interpret it in terms of trees. Instead of considering planar trees, we consider partitions of roundabouts. Well, and here you see the interpretation with operations that are operated way. That's it. This is a formula in genus 0. We have the formula for any genera, and it's much more complicated. But in this case, it's enough. You don't need more. Okay, it works perfectly well. And now that's the last theorem we had for A infinity algebras. And it's going to be my last theorem. We said that A infinity quasi-iso were admitting a homotopy inverse. It's exactly the same thing here. Perfect. This is not in the literature. We have the proof, but this is a paper. We want to add something else. But this is true. So maybe we should, Johan, maybe we should cut and put that on the arXiv. But what I mean here is that if you guys want to prove a formality theorem for bialgebras, Lie bialgebras, pre-Calabi algebras, whatsoever, feel free to use these tools. It works. Okay. So if you want to prove that two DG double Poisson algebras are formal, you can safely compute an infinity quasi-iso from the former to the later, and then you'll get your formality. Okay, so the tools are there, the formulas are there. If you want more details, you send me an email. And this way you can prove new formality theorem. All the conceptual tools are here, and it's completely open to address these questions. That's it. So now it's your turn to play with this. You can use that. And thank you very much for your attention. And if you have questions, feel free.
Thank you. Thank you. Well, I have many questions as usual, but maybe let me ask if anyone has a question before I start asking.
Yes, I do have a question. Can you hear me?
Yeah.
Yeah. I did not see the definition homotopy by algebra. I only see you define like infinity algebra. So do you have that something somewhere in your note?
Yeah, alors, I put in trash bin al by co. It's maybe it's confusing. It's all bialgebras. I just want to call them gebras.
Okay. So this is the same thing.
When I say gebras, you can think bialgebras.
Yeah.
Oh, okay. So can I think this homotopy by algebra just algebra over the Cauchy resolution of proper, something like that?
Exactly. That's how they're defined.
But okay, I mean, I was going to ask about this, so I'm jumping. But now we don't know if V infinity is resolving V algebras, right?
No, but still,
you can define them. You can define them, right?
And they have a nice homotopy properties. Let me see.
But for example, Bruno, can I conclude that a zigzag of quasi-isomorphisms of V algebras is equivalent to a quasi-isomorphism of V infinity algebras? Maybe not, right?
Yes. Give me a second.
Yeah. Maybe for this you need.
What I have in mind. But let me here's what I have in mind. Even if it does not resolve it, there is a map from V infinity to V. So any V algebra is a V infinity algebra.
Yes.
So if you have
oh, maybe then, yeah.
If you have two, no, I think it is true. If you have two V algebras and they're related by an infinity quasi-iso, no, because there might be an issue here. Because the intermediate guys will be in V infinity and they might not be in V.
I see.
Wait, but okay. So I have to think twice at this. But still, for the homotopy transfer theorem, I mean, you see, if we have a V algebra on the big guy, we view it as a V infinity, whether this map is a quasi-iso or not, and then we transfer. Okay, for those of you who don't know what we have been saying here, these constructions, cobar of something, they produce beautiful categories of algebras by algebras because they are cofibrant. They have nice homotopical properties. Being causal means the homotopy theory of V algebras is equivalent to the homotopy theory of V infinity algebras. This is why we lose nothing by going from one to the other. But you see, viewing V algebras as V infinity, yeah, we have all the properties. Am I more clear here?
Yeah.
Yeah, it's clear to me. Thank you.
Yeah.
And because you see, very often people say, oh, when an operad is not causal, a cobar construction of a causal dual is not interesting. No, it is interesting. It's just you're not working with the same homotopy theory and the opera you started with. Okay, why not? But algebras over this guy has beautiful properties.
So, Bruno, do you know a reference, or can you explain maybe quickly the relationship between V infinity and the Frobenius infinity? Or is this something about units and co-units and things like that?
Alors, for Frobenius, you have Frobenius bialgebras or you have Frobenius algebras?
No, Frobenius bialgebras, I mean, Frobenius bialgebra.
My problem, oui, mais alors, hold on. Yeah. For you, Frobenius, they are commutative or not? No, they're not, huh?
No.
Give
Want
me a
to make
second.
it's close to V algebras, right? It's close to
I think it's the conjugal of bialgebra. Alors, give me a
the
second.
Kosul dual of Levi algebra, maybe involutive or
Yeah, interesting. Yeah. For you, I think for you, Frobenius is this, right?
Frobenius is this, yes. Associative, co-associative, and Frobenius, yes.
Yeah. So you see, if you, so the only connection I would see here is that a Frobenius. What do I say? An infinitesimal balanced bialgebra causal dual carries a Frobenius bialgebra structure, which furthermore satisfies this.
Right. No, but I'm thinking, I mean, the cohomology of a manifold is a V algebra, but it's also a Frobenius algebra, right? You think of the Tom form as a pairing, right?
A co-pairing.
A co-pairing,
Yeah. Ah, wait, that
So
way.
that's what I was thinking, more along those lines. So you have a co-pairing and
but again, okay. So in the setting here, I don't think you have enough space to create your product and co-product. But now, if you play with units and co-units, then you'll be able to,
So maybe it has to do with this units and co-units, exactly.
Yeah.
But
yes.
note that having a Tom class, maybe that does not assume you have a fundamental class, right? Like this is less information. Okay, whatever. I mean, I'm asking because there's this paper of Theo Johnson Fried.
Yeah.
I don't know if you remember that he shows. I don't understand the paper, so maybe
I mean, but I didn't work enough, so
so that he tried to lift. He kind of showed that there's an obstruction to lifting Poincaré duality to the chain level in terms of a Frobenius infinity algebra considered as a proper ad, right? As an infinity proper ad. But maybe you can lift it as a V infinity algebra, right?
Maybe.
So
Exactly.
okay, and my last question. Well, I have two questions. Sorry, if you're too tired. You can,
No. It's a pleasure. Go ahead.
So my one question is, this Manning triple perspective, right? That V infinity algebras are, you can think of them as Manning triples of A infinity algebras in some sense. Remember? This is like
because you do A plus A star and you want to do
A plus A
star. Yes, exactly. Yeah.
And do you know if is there a general theory that you can do the same with other operatic structures like B?
There should exist one.
Okay.
I didn't work. Yeah, I remember the discussion. Of course, there should exist. When you look at the roundabout, this is exactly what this has been doing. I mean, look, I'm just doing. If you remove input and output, where can I? I'm sorry for. Okay, no, attends, I wanted a definition. Sorry, here. Yeah, this is a cyclic A infinity algebra. A cyclic A infinity algebra is a bunch of maps, cyclic, and there's no input nor output. In a cyclic A infinity algebra, we have a pairing, and when we have guys, we pair the guys. So there's no need to put input and output. And it is because we looked at cyclic A infinity structures on A plus A star that now we put arrows in one direction or the other. So, I mean, of course, I mean, there's no subtlety here, I want to say. Yeah.
So
and now,
you can probably do this with any operand or any like
cyclic. I would say, okay, something I would like to do if I had time, yeah, is you take a PEEP being a cyclic operand, and you look, Causul if you want, Causul cyclic because maybe you want the infinity versions. So let's say Causul cyclic operand, and you look at what kind of structure you have on A plus A star. And yes, sure, you'll have the same kind of things. Yeah.
But do you need it to be cyclic? Because A plus A star already has a pairing, right? A natural pairing.
Yeah.
So you can ask ask the structure to be compatible with the pair. I mean, A infinity is not cyclic a priori, right? You're thinking of it just as an operand.
No, but I wanted cyclic exactly to act on a guy which has a pairing. So
I see what you're saying. I see what you're saying.
You see, if I work with a non-cyclic guy, why considering A plus A star? You can consider A plus B plus C. Just if you want to A plus A star with the linear pairing, then your operand should come equipped with a cyclic structure to
I see. This is what I was thinking. Sorry. So there should be a notion of like BV infinity Manning triple, an operatic notion, which I think we have examples actually. So that's why.
Cool, super cool. But you know, then there is an issue here is BV is cyclic. There's no problem about that. BV infinity. So the only paper I saw in this direction is the recent one by Villavarer. But it's a difficult problem. It's a more difficult problem. The two models I proposed for BV infinity, noon is cyclic on the nose. Just noon is cyclic. I want to say we were not able to produce a cyclic structure on them. So Villavarer explains that in his last paper, and maybe he has further ideas in this direction. I talked about that with him last June.
Okay. And the last question, this is a quick one. I mean, a quick one in quotes.
The question is quick, the answer.
Do you know if there's a quantization machinery that takes a Lie bialgebra, infinity Lie bialgebra, and produces a homotopical version of a Hopf algebra, extending Etinghoff-Kashdan?
Wait, I would go and look at the paper of Merkulov-Villavarer. They have, I read it a long time ago, so I might take, but definitely there is something there. And for instance, at the end of the paper, there is interpretation of deformation quantization of Lie bialgebras in terms of prop. So this is Enriquez, Albou, Etinghoff. And then Merkulov and Villavarer have been looking at their homotopy version. And it definitely relies on the minimum model of the proper-rad of bialgebras, which exists, but for which nobody has formulas.
This is the proper, like Hopf style bialgebras.
Alors, it's associative algebras.
I
do not mention Hopf because for Hopf we have unit, co-unit, and then with respect to the proper-radic Causul, you see, because we may have maps with 0 inputs and 0 outputs, and this for the theory is not. But there is a technical difficulty here that's I don't want to work in this setting. So just to say, I've been working recently on this minimum model of bialgebras, and I know guys who are working on this with application in symplectic geometry. I'm not super fan of the minimal model. Nowadays, I'm not super fan of the minimal model of the proper-rad of bialgebras. Not Hopf, bialgebras. Okay, maybe one can solve that issue and give me concrete formulas, etc., etc. Okay, but then there is something I don't know how to do. Is that then we know that the minimal model would be the free proper-rad on a homotopy cooperad. Homotopy cooperad. Then it means that, okay, we will have the notion of A infinity bialgebra. Okay, But what are the infinity-morphisms? And nobody will know. The only, you see, because when you create conceptually the infinity-morphisms in all these examples, let me show you. We need that the generator is a cochain, not a homotopy cochain. You see, you know how to split it into two, not now. So if you come tomorrow to my office, and Bruno, I spent the night, I have the formula for the minimum model of the proper derived. It's super cool. It's a difficult problem. But then, so what? You have a infinity bialgebras. But the most you can do is to define an infinity groupoid. No, hold on. An infinity category of a infinity bialgebras, but not a category. So on the other hand, I don't know why nobody wants to study that. I keep saying that to many people, is that why not considering bar-cobar of the properad of bialgebras? The bialgebras, the properad is super easy. You put all your co-products above, you put all your products below, and you compose them in all the possible connected way, period. You see, it's a distributive law. So the properad of bialgebra, I have it. Very easy. And then you take graphs of that, period. This is the bar-cobar resolution. And it's a free properad on a co-properad. I have infinity-morphism, homotopy transfer theorem, invertibility of infinity coefficient. I have everything. So you see, the only obstruction I think is sometimes psychological. Yes, the number of generating operations of this type of guy is big, but completely explicit. And we have all the formulas.
Yeah.
So you see, yeah.
Just a sec. My wife is here, I think. Okay. So when you start talking about the antipode, this is not operatic anymore. This is like homotopy antipode, because this is important for like
I know.
the quantization story, right?
No, it can be. It can be. It's yes, it is properatic or propic anyway in this sense. But the only issue is that so far the theory of properad has been written with the assumption that we have at least one input or at least one output.
Oh, but this is the units and co-unit issue, right?
Exactly. So if you have a unit, no problem. If you have a co-unit, no problem. But here, if you have both a unit and a co-unit at the same time, you might produce maps from K to K with some divergence, etc. I don't claim it does not exist. I'm just saying the theory has been written so far, not including this.
Yes.
Why not? But then you need to you need to go back, look whether you can extend the theory to work in this setting and da. So
okay, good.
It's more complicated.
Yeah.
If you will. I'm
I
not
see.
saying
So,
it's not possible.
yeah. So I mean, just to motivate my questions, because string topology should carry this infinity Lie algebra structure on the equivariant homology of chains, right? And I've always been wondering if you somehow quantize this using some analog of the Etingov-Kashdan thing, you should be able to get manifold invariants from this infinity Hopf algebra. There's because Turaev did this for the Lie algebra of curves on surfaces. He quantized it and he got 3 manifold invariants. Anyway, so I've been thinking about
we
constructing a homotopy version of this story. But it's technical. I mean, there's so many technicalities that it's
yeah, but again, for instance, if you look at this paper of Merkulov and Virvarer, they consider, I think, only the minimum model of the proper algebras. And I mean, I can tell you, last week I wrote in one page the definition of homotopy bialgebras with bar-cobar, and you have everything then. So what I heard is that for people who want to apply this in symplectic geometry, they don't like the shape of the and fair enough, in Morse theory, they say no, because the shape of the operations for us, it's not easy to see why or how to apply them. Fair enough. I'm just saying You see, why doing minimal model? Because, okay, even you can spend 6 months doing it, and then so what? Then it's the generator is a homotopy cooperate. So the best you can do is an infinity category with that.
Yeah.
Which is a bad
I
thing.
mean,
Yeah.
I understand, like, this is what I would want to do it, because then I have some model, and if I'm constructing a geometric structure, I can look at exactly what sort of maps I need to construct, what sort of compatibility. I mean, of course, this is very complicated, but
yeah, it's very complicated. It's
Yeah.
super. But well, there are things which are complicated and things which are not. Just depends what people mean by complicated. It's not a math adjective, but anyway. I mean, for instance, for homotopy bialgebras with bar-cobar, it's huge because we take graphs on. But then it can give you formulas for everything. I can give you formulas for the homotopy transfer theorem, for infini-morphisms. Just anyway, yeah.
Okay. Alex, did you want to say
Is there
something?
time to ask a question, or should I? Hi.
No, sure. Ask a question. Let's.
All right. I have a couple questions too. So first one is about this curvature.
Yeah.
So kind of geometrically speaking, usually we consider when you have a curvature, you put some kind of size. You consider your algebra over like a Novikov field or something, a Novikov ring, and you put a certain description of the size of the curvature. And then you require that the equivalences of such things have some respect this kind of filtration.
Yeah.
What I wanted to ask you is, you said that when you put the curvature, all of these become the same notion. But is it the case that to go between one and the other, you need to consider like a isomorphism that does not respect this kind of size? This is kind of geometrically what I would expect.
I'm not sure. I see what you mean. Which is absolutely true is that when we work with curved homotopy, blah blah blah, we need something that I did not require before, is a complete filtration, etc., to accommodate the series that appear. So this is, I didn't say, but yes, for sure. I mean, when I mentioned curved algebras, I definitely want to say that we worked under the assumptions that we are in a complete setting with respect to a certain filtration, Novikov, but any general thing. So does this answer your question?
I guess my question was that are these canonical isomorphisms something that kind of respects this filtration, or is something that it's just hard to me to see how like adding the curvature makes them
no,
the same if they were not the same before.
Give me 1 second. No, in the dioperas, in the properades or dioperas themselves, there's no filtration completion. In the properades themselves, no. It's when they act. When they act, we need to have a complete chain complex, etc. But no, on the properades, I don't see that. Give me a second. I don't think I need that. No. I split into. No. I need no.
Alex, in what setting do we work? Curved or non-curved?
Non-curved, non-curved. Yeah.
You're lucky, guys.
I mean, you could work a curvature too, in this. But then in geometry, usually you have you want to put a certain filtration of the curvature. It's I think somehow in this non-commutative geometry picture, if you have like a curved infinity algebra, right? You can imagine as like a vector, like a non-integrable kind of homological vector field. And if you have curvature without any restriction, you can always come up with a quasi-isomorphism that makes it trivial, right? You can like straighten up the vector field. So I would imagine that this isomorphism comes from the same type of thing. You can like partially straighten some of these multi-vector fields.
maybe conceptually.
For that, you would need to have something that kind of does not respect the filtration. I don't know. I mean, that's kind of just intuition, but I would need to see exactly how the isomorphism works.
From the properadic point of view here, there's no filtration on these properades, etc. It's just by adding the curvature, you're adding a guy with 0 input and 1 output. And then this kills the difference between all these operations. Okay. A priori, double Poisson has no operation with 0 input. Infinitesimal bilength bialgebras have no operations with 0 input, but your pre-Calabi they do. But now if you put the curvature will allow you to kill some inputs here and kill some inputs there. That's why then they're the same.
Right, yeah, I see. Yeah. I guess my question is like, is it the same phenomenon as when you put anyways, we can chat more about this later.
Let me say something from Manuel. Now we are looking at curved version, which means that on the causal dual level, we have unital version because the causal dual of curvature is unit. So here now, if you put a unit here, you put a unit there, and you put a unit there, boom, they are all isomorphic. Maybe it goes more in the direction of what we said before, okay?
Yes.
Adding a unit here, and there, boom, iso.
I mean, Alex, we're not in the curved version. I mean, I'm thinking for string topology and so on. When you cook up this V infinity structure or pre-Calabi for a manifold, this is non-curved, but we do care about units, right? About
we could have it non-util too. It doesn't matter. Yeah.
but the homotopical theory is different. If you have
it's true. It's true. Well, we can maybe fix it by adjoining unit and killing the right thing off.
And also, I have a question for maybe Alex and
yes.
Do you consider higher genus pre-Calabi algebras with Maxime?
Yeah, so this actually that's another question that I want to test as to Bruno, which is that I guess we see pre-Calabi as something that's defined using like the moduli space of certain moduli spaces of disks. Right, that's how he visualizes. I mean, it's like symplectically speaking, you should get it from looking at certain moduli spaces of disks. And then the result in our paper is kind of like a con extension result is that whenever you have that, you can always con extend it to an algebra over this big prop, which is of all like marked Riemann surfaces with all genera.
But that's sort of a trivial extension, right?
I mean, I don't know what that means.
Like you're saying, so what's the statement for algebra at the algebra level? Like every
algebra over this was dioperad, I guess Bruno called the co-dioperad of disks with
right,
multiple inputs, multiple outputs, lifts to an algebra over the big prop.
Right, but what I'm saying is that this algebra over the big prop will not have more information.
Yeah, it doesn't have more information. That's right. So this is kind of what I want to test. Like when you say you have the formula for the V infinity higher genus, I don't really know what that means kind of geometrically. I would imagine that it's the same thing as V infinity in a sense, because the information contained by this higher this like prop of all Riemann surfaces with marked boundaries, etc., is the same information as contained just with the disks.
But the homotopy theories of these algebraic structure are not equivalent, right, Bruno?
No, that's
V infinity as a dioperad and V infinity as a properad.
No, they should not be the same or not. What do I want to say? If V is causal the properad, then V infinity with all genera. No, they should not be the same.
They're not the same,
No,
right?
they should not be the same.
I guess it's not just what V infinity in all genera means even, but it's
it has more relations, right? Like it's the algebraic structure with more structure maps and more relations.
Exactly.
Like
you see,
I think if maybe if you construct this for a manifold, if possible. Maybe it has even more information, you know, because it has more structure.
It should,
But
it should.
what is it? Is it what is it? I guess kind of a maybe question which does not have an answer in this case, but does it come from geometry? Is it chains over any geometric moduli spaces?
Oh, well, I don't know. No,
Okay.
the way we use it with Johan, or I mean, I think that's what Kate, etc. looked at. Is no, you start from a say dioprad, okay, and then you cook its causal dual, and then when you cook it within the world of dioprad, you just consider graphs of genus 0, and you get this pre-Calabi your co-dioprad, etc. Now you say, no, there is a world where you can allow yourself to have more kind of compositions, not only graph of genus 0. And then in this context, you have the causal dual. And then you have more guys there. So the causal dual as a properad has more operations. You have operations with genus, okay? And no, the way I understand producing it is just by this algebraic device, which is causal duality, blah. I have no geometric model.
I see. Well, but the geometric model also has operations with higher genus, right? You can just compose these, you get this like quivers, but this kind of.
But this higher genus is meaningful. It's not created for free. It's produced by causal duality. It's not a kind extension. You can always take a dioprad and take the properadic envelope. Is like maybe if you know the modular envelope of the cyclic operad. You really create the genus. You can do the same thing from a dioprad. You know how to compose two guys along one edge, and then you can take graphs of that. But as Manuel was saying, this produce no more constraints. I'm not doing this. I'm producing more homotopies via causal duality. So I'm creating a bigger guy here. You see, I'm creating a bigger space of.
I see. Yeah, no, I mean, I mean, just from geometric intention, I would expect the statement to be that when you do this, in the end, you may think you're getting constraints, but because of this, the description of these moduli spaces, you end up not. I don't know. It's a good question.
Maybe if we finish the computation of the causal dual of V in any genus, then we can show them, and then maybe you will recognize something, the dimensions, the shape, the blah blah blah. Maybe it will give you a flavor of a geometrical guy.
Okay, well, thanks anyways.
You're welcome.
Thanks.
Sorry if I did not cover faithfully all your paper. I wanted to
it's fine. I mean, this is about other things too, and it's interesting to see another perspective. It's
you see, there is something I wanted to explain here, which is I think badly explained in the literature, is why on the strict level there is no map, and when you pass to the homotopy level, yes, and it's exactly because of that. You see, on the causal dual level, you have a map which sends a generator to the composite of two. So it's not a map of quadratic data, and this allows us for more freedom. I like this interpretation very much. This is how I understand the statement now. So.
Okay, I have to pick up the other Bruno.
This is important. Okay, have fun playing soccer with it.
Thank you so much for this. This was recorded. I can share it with anyone if you wish, or with you, or whatever. And
yeah, Alexandre wants to see it, Kene, and I will review the few typos I saw, and I will send you a version that you can put on any website. It's free, etc. Let me review. Don't put the one I sent you. Let me review it because.
Okay. Yeah. I will wait.
Are you going to publish it to YouTube, Manuel? So
yes, I can put it. I can put it on the Purdue Seminar channel. Yeah.
Yeah, okay. Good. Thank you. That's our next talk. Yeah.
Okay. And if people have questions, send me an email.
Yeah.
Well, not too many emails, but send me. Enjoy, guys.
Thank you so much, Bruno. Good night.
Thank you. Thank you for the invitation. Thank you.